questions to get through and then one discussion if there's time. So in this one, we have a 150 watt incandescent lamp light bulb with the filament. Filament has a diameter of 0.5 millimeters, and then we also know the diameter of the glass, so we're assuming that this is kind of a circle. We want to know, determine the heat flux on the surface of the filament and on the surface of the light bulb, and then we want to calculate how much energy per day. And so the two kind of important pieces of theory here, the first one is defining, I guess, what we're talking about. So typically we'll write heat like this. So this we call heat transfer. And this is in rate because we have the dot. And then we'll also talk about heat flux, which is the Q dot per unit area. So that's the first concept, is just these definitions. And then the second concept we need to know is from thermodynamics. We generally know that any Q into something is, or minus the Q out of something, is going to be equal to the change of energy within that spot. So if you have a can of Coke and then it loses a bunch of energy to the air, then it's going to emit heat or lose heat to the air. And then I guess Coke, or for coffee if you're losing heat, and that's going to be represented in the energy in that liquid. And typically we're talking about steady state. I should put a dot in here. So when we first turn on this wire, the wire will be cold, and as we turn on, it'll be hot. And so there'll be some energy change within the wire. But once it's on for a little bit, it's going to kind of reach equilibrium. And so it'll start emitting the amount of heat, and there's going to be no change of energy within this wire. And so with steady state, we're usually dealing with Q in is equal to Q out. That's what we're going to look at for this question. So for part A, make sure it's not a large screen. So we're looking for heat flux, so that's watt per meter squared. So that's this one, and I've missed a dot there, of the filament. So we're looking for Q dot of the filament. And we'll just go back up to for a second. We know 150 watts, so we know how much energy is being put into this light. And we know the area. And so we should be able to figure out the heat flux. And we also know, okay, so that'll be for part B. So the first thing we'll do is we'll calculate the area, the surface area of this filament, which we know is pi dl. So the circumference times the length, which is equal to pi 0.5 centimeters times the 5 centimeters. This is equal to 0.785 centimeters squared. Okay, and so now once we know the area, we can find the heat flux. So one of the important concepts that this is testing is that first law, which is everything in has to leave. So we have this wire, and this will be grounded, and we know that we're putting this energy into it of, or sorry, I shouldn't. We're putting this kind of energy into it of 150 watts. And so because we know this, we know that actually the amount leaving in terms of heat transfer is also 150 watts. And we know this because essentially everything that goes in has to come out. So of course the goal of a light bulb is to light, but the amount of energy that's required to create that light is actually very small. And that's why we're able to have LEDs now that are so efficient. But we make this assumption that essentially everything going through this wire is becoming heat. And so what we're interested in is the heat flux, which is kind of the per area version of this Q. So that is equal to 150 watts over that area we just calculated, which is 191 watts per centimeter squared, which is 1.91 times 10 to the 6 watts per meter squared. Okay, so that was part A. We wanted to find heat flux of the filament. I guess any questions on that? Okay. Again, feel free to just unmute, or you can also ask questions in the chat. I should make sure that I'm monitoring that. Looks like. Okay, that's fine. I'll try to put that on my other screen here. Sorry, one more second. Oh wait, not everyone can see it. Okay. Okay, so part B. Is the heat flux of the glass bulb. So now we're looking for this, actually the same quantity, but now we want for the glass bulb. And obviously we don't know this right away, but we do know something. So we know that we're putting this 150 watts, and we know that that means it's exiting this wire as heat. And so by that same assumption, so we're putting in 150 watts into this wire that's then attached to this light bulb. That's the worst light bulb I've ever written. And so we know there's the way that heat transfer moves from this wire to the air, the light bulb to the air is actually quite complex. There's convection to this air, to this, and then there's conduction through the glass, and then there's convection on the other side. So this way of the way heat transfers would be quite a complex analysis, but we are able to say the same thing because we're assuming this is in steady state. So if we're putting this into the light bulb, into the wire, and we're assuming it's exiting the wire, we also are going to have to assume that it exits the light bulb. So the idea is that our Q dot here is also 150 watts. So Q dot is equal to, so this time we're actually doing the area of a sphere. So the equation is slightly different, but the concept is the same. So we're using the same equation. We know our Q dot is 150 watts. We know our area, 201.1 centimeters squared. And it gives us 0.75 watts per centimeter squared. Okay, so not necessarily the way I would normally do the units. I am working off of an answer key. but we'll leave that up to you. You guys are in 4th year now, so had a lot of experience dealing with units. Okay, and then the last part was the amount of electricity, or the cost of electricity assumption consumed over a 1 year period. So we'll just go back to the question one more time. And me jumping around so much is making me realize it's pretty important for me to post this, because this may be hard to follow if you're taking notes. So I'll try to do my best for that. But we do know that the cost, so we wanted to see for 8 hours a day, every day, with the unit cost of electricity 0.08 kilowatts per hour. So cost per year, and we're assuming 8 hours per day at 0.08. Or it's dollars per kilowatt hour. Okay. So the electricity consumption. Ooh. Oh, yeah, sorry, I'm seeing in the comments. Okay, I know technical difficulties are frustrating, but I did lose the video for you guys for some reason. Can someone just put on the chat if you can still see me? Or, sorry, still see my screen? Yeah, okay. Maybe everyone quit their video and that's why. I'm not sure. Okay, anyway, I'll just continue. So electricity consumption, yes, so there was a question in the chat. ID squared. Okay. Sorry, there's something in the chat that's it's pi d squared, and so there is pi d squared there. Maybe I didn't write it at first. Maybe that was an old chat item, but this shouldn't be pi d squared. This one's pi dl, because this is the circumference times the length of the wire. Okay, continue on. So the electricity consumption is equal to Q dot, so how much electricity is leaving the bulb, times how much time we're talking about. So in this case, we're talking about 0.15 kilowatts times our amount of days, and then times 8 hours per day. And this will be equal to 438 kilowatt hours per year. And I guess just as a note, this kilowatt hours, it's kind of a weird unit because kilowatt is per time. So a watt is a joule per second. So, and then we're multiplying it by hour. So this is not typically what we find in SI, but this is typically how electricity is seen on your bill, and it's how it's charged. So you can see that our price, this would actually be how you would see it from your utility data. So it's quite a useful metric. It's just a little easy for us to understand as people. So just so you're aware of why that is. And so the annual cost is that 438 kilowatt hours per year times the 0.08. Kilowatt hour, which is 35.04 per year. Okay, so that's the answer to this question. So we'll just get maybe a quick in the chat if I guess that makes sense. And if the pace that I'm going is okay, or if you have any concerns about how I'm moving around the screen. Okay. And so I guess the professor asked me to just make some comments on how all this relates to buildings. You'll notice that a lot of these examples don't, but it all does matter. So this assumption that a lot of the heat will go into, or a lot of everything we put in this bulb will turn into heat, is actually interesting because it means that super high efficient light bulbs aren't actually always the best decision. So in my apartment here, it's all baseboard heating. So actually a light is just as efficient at heating the apartment as my baseboard heater. So it's just something to think about. So they're maybe not so good in the summer, but they're almost even a good thing in the winter because they're dual purpose. But in larger buildings, usually you're talking about things that are much more efficient than baseboard heaters, and so usually it's a pretty good cost-saving measure to change your light bulbs to LEDs. But one interesting way it interacts is in Ontario, where they have natural gas. The heating that's provided through the light bulb is usually cleaner than that provided through natural gas. Though the heating provided through natural gas is much cheaper. So when a building switches over to LEDs, they're usually reducing their price of operating their building super significantly, but often it'll actually increase GHG emissions very, very slightly. So hopefully that's a little interesting. Okay, so we'll move on to the next question. So this one is about, this one's about conduction. And we have a pipe. We have a uniform heat flux. So this time we actually don't know the full Q, but we know that kind of smaller Q. And that's 60 kilowatts per meter squared. Okay, and then we know the inner diameter and the outer diameter and the wall thickness. And for safety reasons, we don't want the outer part of the container to get over 50 degrees Celsius. We know the ambient temperature is 23 degrees Celsius, and we want to determine the necessary convection heat transfer coefficient to keep the container's surface out of 50 degrees Celsius. So this question I find is asked kind of in a weird way. I think maybe that's why it's a good tutorial question, because it's maybe a little weird. But so I just very quickly want to cover how you normally do convection, which is you have some outer temperature. So in this case, we're talking about 23 degrees Celsius. And we know that heat's going to be emitted through the air. And sorry, we know that we need it to be 50 degrees Celsius. That's the surface temperature. And the way that this kind of transfers to the air, it's going to depend on this difference of temperature here and temperature here, but it also depends on H, which is the heat transfer coefficient. So for conduction, it's K, and for convection, it's H. But H is actually a little more complicated than K. K is a property of the material. H is a property much more of the conditions. So the fact that it's air is going to be one of the things that factor into H, but also maybe how much wind there is here, and the way in which the air is interacting with the surface also matters. And so that's why you'll see stuff like fans in your computer, because that's going to increase this coefficient. So for the first little bit of the course, this is going to be given, but later we're going to understand how that's calculated. And so the general convection, which you've seen, is equal to HA, and then usually we'll say T surface minus T infinity. And infinity is just far enough away from the pipe that you've reached ambient conditions rather than, because right here, for example, it's still going to be hotter than out here. So it's just kind of when you reach this farther point. Okay, all that said, the way we solve this is we know this heat flux on this inner surface. We also know this diameter and this thickness. And so we can actually find heat flux on this outer surface. And we can use that to calculate the H that we need. So hopefully you'll see that more clearly as we work through the problem. So the first thing we need to know is that this Q in, and this is Q in to this metal pipe specifically, is equal to Q out. So this Q in is represented by this heat flux that we know. And so because we only know the heat flux in the area, we'll just separate this out into those two things. This is area of the inner, and this is the heat flux given. And this is going to be equal to whatever happens with this convection, because this is going to be, because this is going to be where that heat is coming out. So we have H, A of the outer surface, and then this Ts minus T infinity. And in this case, we know Ts, we know T infinity, we know A out, and we know A in, and we know this heat flux. So we can see that if we just reorganize this equation, we'll be able to find our convection coefficient that will give us this condition that we need. The condition being that our surface temperature is 50 degrees. Okay, sorry, my computer's fighting with me. This is something to prepare ahead of time. It doesn't like to scroll down if there's nothing down there. Okay, so we'll expand this a little more. Our Q dot on the inside times pi d squared is equal to our H and then our pi d squared on the outside. And then when we reorganize this, we'll have the pi's cancel out and we'll reorganize for H. So this is equal to our Q dot Ts minus T infinity. And then just our differences of diameter. All be squared. Okay.
Can you please just go up a little bit?
Yeah. Is that enough?
Yeah. What's the line on the first line?
This one?
No, the one above it.
Oh.
Yeah.
Oh, this was just what our given was for our heat flux. Oh, and it's not, right? Maybe that's why you're asking.
Yes. Okay, thank you.
Okay. Okay. So this 60. We'll do a little unit change there. And then again, our 50 is that surface temperature we're trying to get. So essentially, we're trying to create the conditions of H such that this outer layer will be 50 degrees Celsius minus 23. And then the units for this are actually delta degrees Celsius. And then our inner diameter was 1 meter. And our outer diameter is going to be 1 meter plus 2 times the thickness because we're dealing with diameter. squared, which is 1840 watts per meter squared Kelvin. Okay. So this is what our H, if our H is this in this problem, then we're going to get exactly 50 degrees on the outside. But the question is asking, because it's a safety issue, we want something lower than 50 degrees Celsius on the outside. So I guess the question I'll just ask, and you can put it in the chat, is does our H need to be larger than this or smaller than that to get less than 50 degrees Celsius?
Larger?
Larger, yeah. And we can see this mathematically by looking at our convection equation. More H will mean more heat transfer. And we can also just understand it intuitively. If we're trying to cool down our pipe, we want a higher convection coefficient. And one way to achieve that would be by blowing a fan on it or something. If we were trying to aim for this, we could do it that way. So say H should be larger than 1840. And of course, if you didn't know, you could just plug in some answers and try to see what works.
I have a question.
Sorry?
I have a question.
Yep.
Heat transfer, the Q dot in, is that heat transfer by conduction?
Yes. So this is some chemical in here. And so the way in which, so I guess just to be sure we're labeling this properly, what's leaving this pipe, this we're calling Q dot out. And what's going into this pipe, this we're calling Q dot in. Where the pipe is kind of the center of attention for this equation. And so this Q dot in, because this is a chemical and because it's a liquid, it would be with convection. But we're given heat flux, so we don't need to do the convection equation. That's kind of already done for us, and that's this problem. Does that answer the question?
Yes, yes. And for the area, the D in and D out here, you wrote that radius?
Yes.
Okay.
So again, the pipe is the star, this is D in, and this would be D out from the kind of center.
So D here, D in here, do you put 1 meter or 0.5 meter?
So D in was 1 meter, and then D out was 1 meter plus you have to 2 times the thickness, which is where this 2 times 0.05 meters came from. All right, and then that leaves us with about 10 minutes to answer the last one, which I think is pretty reasonable. Okay, so we have 2 surfaces. One is highly polished and the other is oxidized. And they're found to be emitting the same amount of energy per unit area. The highly polished surface has emissivity of 0.1, and we know the temperature is 1070 degrees Celsius. Well, the emissivity of the heavily oxidized surface is 0.78, and determine the temperature of the heavily oxidized surface. And so again, this one is also kind of a weird question. It's not your typical radiation question. And I'm just going to explain very briefly what this is talking about. So typically when we have a radiation question, we know the temperature of our surface, and we know the temperature of our surroundings. And we say that we're going to describe our heat transfer as emissivity, Stefan-Boltzmann constant, area, and then our T surface minus T surroundings. And both of these are going to be to the 4. And so this is normally what we're used to dealing with here, but we're actually going to go one step back for this equation. And so the weird thing about radiation is that it's not the same as with convection or radiation. With convection or radiation, the heat transfer is driven by the temperature difference. Now with radiation, it's much more that each surface, every surface is just emitting. So there's actually a Q emitted, and this is the first part of this equation. So basically, no matter what temperature the surroundings are, it's just going to be pumping out this much energy. And then it's also going to be getting in energy from the surroundings. And this is going to be, you know, the other part of this. And usually what we're interested in is the difference, which is why we end up coming to this equation. But if we read this question, it's asking very specifically, two surfaces are found to be emitting the same amount of energy. So we're actually only going to deal with this emissions part. So again, a bit of a weird question, but it's important to understand that. So we know we can define our emitting by this equation. And actually, I've missed the areas in these. And then we know that for these two surfaces, we're going to say that the Q emit of surface 1 is equal to the Q emit of surface 2. Meaning emissivity of 1, and then area of 1, S of 1 to the 4. Okay. And then we're told two surfaces, so they're giving the same amount of energy per area. So actually I probably should have rewritten this as the Q dot, so the small q emit 1 is equal to the small q emit 2. So actually we're going to include that as a step. It's a little messy. And so we're looking at the small q, it's per area. So I'm going to use that step as the reasoning to remove this area. So let me know if that's not clear. And then the Stefan-Boltzmann constant cancels, and we just end up with emissivity 1 Ts 1 to the 4 is equal to emissivity 2 Ts 2 to the 4. Okay. And then we just reorganize this. So what we were trying to find was this temperature of our second surface such that it would emit the same as our first surface. So Ts of our second surface, that's what we're looking for. And this is equal, oh, actually, so just say one step here. So you'll notice that this has this plus 273. So we need to convert to Kelvin. Anytime we're dealing with radiation, we're dealing with this to the 4. And so we're always going to have to use Kelvin. And just as a general rule, the reason why we're able to use degrees Celsius in the other questions is because we're talking about a difference of temperature. So we can think of it as like the difference of 1 degree Celsius is equal to the difference of 1 degree Kelvin. That's how it's defined. But here we're not talking about it. We're raising it to the 4. And so as a good rule of thumb, if you're ever wondering, Kelvin is always safe. If you convert stuff into Kelvin, that will always work. And so if you've done it in Celsius and you're questioning whether or not you were allowed, and you do it again in Kelvin, you get a different answer, then the Kelvin one is correct, and you would have wanted to use that from the beginning. So this is 803.6 Kelvin. Okay, and you can maybe put in the chat. This all makes sense and is good.
Yeah, all good, thank you.
Okay. So 2 minutes to spare. Oh, so I guess, again, just to bring this back to buildings. So radiation actually has a pretty big role to play in buildings. I'm sure you guys have seen that already. So the way we notice, I guess, as humans radiation, normally it's this very small number multiplied by these temperatures that are to the 4. And so there's a really big difference here. Then this number can get really large. But if this difference is small, this number is pretty small. And so the effective radiation is pretty small. So if we're like sitting by a campfire, the difference is very, very large. And so we'll notice it. But in buildings, we don't always perceive of it. But it is actually very important. And one of the examples is with large windows. Often if you have large windows, even if your feeling is that you're warm, or even if you feel that you're warm, or sorry, even if the air temperature is warm, you may feel cold just because you're losing heat to that window through radiation, if it's a cold day. So the last question is a discussion. Is it necessarily to ventilate buildings? What is the effective ventilation on energy consumption? And is it a good idea to keep the bathroom fans on all the time? So I guess, does anyone want to try to explain this? That's a very broad request for input. I mean, one at a time. Like, why is it necessary to ventilate buildings? Does it have to do with thermal comfort for heating? You can put answers in the chat as well.
Air quality and thermal comfort.
Right. Okay. So yes, and the main thing is air quality, and a lot of times people will combine the thermal comfort and air quality systems. But again, if you think about my apartment, there's no ventilation; it's all kind of naturally ventilated, and we're still able to achieve thermal comfort. But that ventilation, you're taking out air that's conditioned, that's warm, and you're bringing in air from the outside that's not conditioned, and so that affects energy consumption. And with bathrooms, usually, so with normal offices, usually what you would do is recirculate some of the air, so you're not having to recondition all of the air. But with bathrooms, normally they don't. They'll send it right outside. And I'm sure you guys have seen a lot of that in your other classes. Okay, and that's pretty much time. So feel free to go. And if you have any more questions, I can stick around for another 5 minutes or so. But thank you for attending.